welcome back to the webinar. We will get started with our 12:30 presentation. We'll be hearing from Allison Hahn, the Light Water Reactor Sustainability Program Manager. She will be presenting scopes RC-7 through RC-9. Allison, can you hear us?
Yes, I can hear you.
Okay, we can hear you. You can start when you're ready.
Great. Can you see my screen?
Yes, we can.
Perfect. All right. Thank you, everybody, for calling in today. I am Allison Hahn, the Program Manager for the Light Water Reactor Sustainability Program. So I will be going through, if I can, there we go, an overview of the Light Water Reactor Sustainability Program before I get into just a high-level summary of the individual work scopes in each of the areas that we have today. So when the LWRS program was initially created about 10 years ago, sustainability was defined as the technical basis to get these plants to operate from 60 to 80 years. And through research with a number of research organizations, the community concluded that there are no significant material concerns to get these plants to operate to at least 80 years. And that's evident with the number of applications for the subsequent license renewals, with more being announced, their intent in the coming year or so. So we had seen that milestone coming, and the LWRS program worked directly with the utilities, owner-operators, and vendors to see if there was a new definition for sustainability related to the existing fleet. And we came back with the understanding that it was now focused on economic factors. And again, that's evident with the number of plant shutdowns in recent years, that some were based on policy decisions, but also a lot of them were based on economic factors as well. And so we have a number of areas within the LWRS program looking to address those economic concerns. You can see here the 5 areas within the LWRS program that we are currently working on. You might recognize plant modernization, risk-informed systems analysis, and materials research. Those are the areas that we have worked on in the past and have reconfigured slightly to address the economic concerns within those areas. Those are the 3 areas that we have work scopes in for the FY20 CI&R solicitation. We also have 2 other scopes that began in FY19 this past year. The first is flexible plant operation and generation. This area is to evaluate and demonstrate integrated energy systems to produce, of course, electricity, but also the non-electrical applications that might be feasible, such as hydrogen for the surrounding area, transportation fleet, or metals refining, things like that. We're also looking at desalination. Work in this area was started through the cross-cutting technology development a few years ago, and the LWRS program has just recently picked that up and been looking at for the existing fleet. To the right of the slide, you also see physical security. This is a brand new area for us. It was just started in FY19. We're wrapping up that initial year of planning and looking at the R&D projects that we can move through. But the pathway itself will validate methods and tools to update the physical security regime to optimize physical security at the existing fleet. So this is a brand new area for us, and we're really excited about the R&D results that we should be seeing in the next couple of years or so. So the first area I'm going to talk about today is the plant modernization research. This pathway is working to significantly reduce the risk of the I&C modernization. The strategic goal is to extend the life and improve performance of the existing fleet through modernized technologies and improved processes. This will be accomplished by first demonstrating and validating new technologies and operational concepts at host nuclear plants, by also providing the technical basis reports to support long-term planning, procurement, and regulatory submittals, and then lastly by providing guidance for full-scale implementation and communicating those results to the other nuclear power stakeholders. This area is not trying to simply replace analog with digital technologies on a like-for-like basis. Rather, we are working with asset owners and vendors to deliver greater functionality, higher reliability, improved situational awareness, and a technology base that is also more affordable and sustainable over the life of the plant. We are working with an industry working group to identify the biggest challenges and opportunities where R&D can have the greatest impact. So the work scopes in this area, there are 3 work scopes under RC-7. 2 are on this slide, there's 1 on the following slide. So the first one is the digital instrumentation and control. This one's looking to develop an automated or semi-automated means of converting analog circuit design information to their equivalent digital system function block logic. So in addition to major reactor control and protection systems of operating nuclear plants, there are thousands of discrete analog control circuits for the balance of plant systems that must also be converted to software if the plants are to be fully modernized, and the associated O&M cost reductions are to be obtained. The development and verification of software equivalents of these analog circuits is tedious, time-consuming, and expensive. It is also highly susceptible to copy and translation errors. However, most of these discrete analog circuits are customized variations on basic control schemes for standard components such as air-operated valves, motor-operated valves, pump motors, and fan motors. And most nuclear plants have some form of computerized drawings for these analog circuits, creating the potential for an automated or semi-automated means of generating the equivalent software logic. This technology would read or process these computerized drawings to identify the basic circuit type, the presence of circuit customizations, and then the specific device and circuit identifiers by converting this circuit information to equivalent control software, for example, the function block logic of a distributed control system. The intended outcome of this project is the development and demonstration of a prototype application for rapid, accurate conversion of these discrete analog circuits into control software modules that can then in turn be tested for accuracy in a plant simulation environment and ultimately be used in the actual plant digital control system. So that's the first work scope. The second one is the virtualized distributed control systems for nuclear power plants. Current distributed control systems have employed IT virtualization software at the supervisory control and HMI portion of their architectures. This has eliminated the need for purpose-built hardware previously used to perform these functions. This has drastically reduced the physical footprint of DCSs and lowered their costs. It has also protected the intellectual property investments made in software, which can be migrated to new hardware when required by obsolescence. This significantly reduces obsolescence risk and also life cycle support costs. DCS vendors have not yet been able to fully extend virtualization to the individual. Physically distributed process controllers loaded with application-specific software affect control of plant equipment to which they are connected. R&D is sought to provide successful DCS virtualization at the process controller level, which would provide an extension of the benefits of virtualization realized at the supervisory and HMI level. This fully vertical integrated solution would provide a degree of software independence from hardware not previously achieved. Controller application software would be essentially decoupled from hardware obsolescence. This software could also be directly ported for use in plant training simulators. It could also be used for development and evaluation, both for INC design changes and for new INC functionality in a virtual environment. The R&D results should include research needs to ensure attributes such as function segmentation, determinism, latency, control failover, and also system health checks are retained, and any novel failure modes unique to a virtualized architecture are identified and addressed. In addition, critical attributes of current DCS controllers and the way they communicate down to field input and output devices and up to HMI and supervisory control portions of the system architecture need to be evaluated in this virtual architecture context. So then the last work scope within RC-7 is this one here, reducing human factor uncertainty using artificial intelligence in operation and maintenance of nuclear power plants. So in a nuclear power plant, skilled field workers perform numerous non-destructive evaluations, testing, inspections, and calibrations. These tasks are performed under challenging operating conditions, such as temperature and radiation. At the same time, field workers are under psychological pressure to perform assigned tasks to the best of their ability and within specific time requirements and technical specifications. Human factors aspects play a critical role in setting up the tools to perform measurements, interpret the measured signal, and record the assessment. There are potential for error, variability, and uncertainty at each stage of that task. This effort is time-consuming, laborious, inefficient, and expensive. To support the program mission to reduce operating costs using technology, the pathway is seeking proposals that would 1. Provide innovative solutions to automate several of the operation and maintenance activities, develop explainable artificial intelligence and machine learning techniques to analyze and interpret the measured data, perform on-site diagnosis of any potential issue, perform prognosis of potential future state, and provide appropriate recommendation action. And then lastly, the proposal is encouraged to demonstrate the developed innovative and scientific concept in a representative environment. So Those 3 work scopes were assigned to the plant modernization area. I'm going to move into the risk-informed systems analysis area now. This pathway of the LWS program provides tools and methods to inform nuclear power plant margin management decisions with a focus on improved economics and reliability. The R&D project products will be used to optimize plant economic performance and safety by incorporating plant impacts, physical aging, and the degradation process. These tools and methods were developed with a focus on coupling the risk assessment or the probabilistic and systems margins quantification or the deterministic to achieve realistic modeling and representation of margins for the long-term benefit of nuclear power plants. The implementation strategy of the RC methodology focuses on industry organizations' participation in the pilot demonstration projects addressing key issues relevant to the nuclear power plant. So within the RC area, we have 1 work scope this year, evaluation of physical phenomena, data, impact, and improvements. Modeling the effects of physical events such as fire, flood, and high winds in nuclear power plants risk assessment involves using data and guidance that is typically conservative based on historical experiments that were performed before advanced measurement tools and controlled environments were available. This causes a number of uncertainties and conservative decisions in response to those knowledge gaps. The research requested in this work scope should include 1. Perform data analysis on the data used in hazard guidance for phenomena-driven areas. 2. Develop advanced uncertainty quantification and sensitivity analysis methodologies to determine significant contributors to the uncertainties. And then lastly, perform design of experiment analyses to identify new high-value experiments. The last area that I'll discuss today is the materials research area of the LWS program. This pathway within the LWS program has the goal to understand and predict long-term environmental degradation behavior of materials in nuclear power plants, including detecting, characterizing, and mitigating that aging degradation. The pathway has been focused on 4 main principal areas: reactor metals, which includes RPV steels, mechanisms of IASCC and SCC initiation in nickel-based alloys; concrete degradation, which includes radiation and environmental induced damage, ASR, and then NDE techniques to characterize that degradation; cable systems, to include mechanisms of cable installation, aging, and degradation, and NDE techniques to identify those mechanisms; and then lastly, mitigation technologies, which includes advanced weld repair techniques, and then also the potential for advanced replacement materials. These are all tasks that were identified as priorities in the expanded materials degradation assessment. Materials research pathway tasks support collaborative research with industry and/or regulators. The focus of these tasks is on supporting and extending industry capability by providing expertise and unique facilities or the fundamental knowledge in the form of data analysis techniques or predictive models and code. So again, this area has 1 work scope tied to it, elucidating how the water chemistry affects the corrosion sensitivity of stainless steel in nuclear power plants. So the chemistry of the coolant water and pressurized water reactors plays a major role in corrosion and integrity of pressure boundary materials in light water reactors. And then stainless steel is a common material used in structural and core internal components in nuclear power plants. Stainless steel features excellent corrosion resistance because of the formation of passivating oxide films on its surface. However, that passivity breaks down can render the material susceptible to corrosion-related degradation. Lithium hydroxide has been used to control the pH of the water and reduce corrosion. However, a limited number of vendors exists for that nuclear-grade lithium hydroxide. Potassium hydroxide can potentially substitute for lithium hydroxide, but its effects on corrosion behavior of metal components are not well understood. Potassium hydroxide is an economical alternative to lithium hydroxide and at least 5 times cheaper. Replacement of lithium hydroxide by potassium hydroxide will result in reductions in the operating costs, which can then be passed on to the end consumer. This call seeks to develop a new understanding of alkali effects on corrosion behavior of stainless steel. So that is all that I have for my presentation today. I can answer any questions related to the broader program, but we also have the technical points of contact for each of those work scopes on the call today and can answer any technical related questions that you may have.
Thanks, Allison. While we start taking questions, I am going to unmute the technical points of contact. Craig, are you there?
Yes, I am.
Okay, great. We can hear you. Craig is TPOC over the RC-7 areas. I'll also unmute Hongbin Zhang. Hongbin, are you there? Oh, it appears that his audio, oh, Hongben, are you there?
Yes, I'm here.
We can hear you.
Okay, good.
He can answer questions on the RC-8 area. And then we have Frank Chen. Frank, are you there?
Yes, I'm here.
Okay. Frank can answer questions on the RC-9 area. So we'll start, I believe, on the RC-9. What is the meaning of pristine? Is there a specific steel alloy in mind? And does it include nickel-based alloys?
I think pristine here means it's non-irradiated materials. I think we are looking for particular stainless steel used in the structure and internal parts of PWRs. Nickel-based alloys, it can be also in the consideration.
We'll stay on the line for the next minute or so. Please do submit your questions now if you have them. Allison, is cybersecurity a consideration for the plant modernization R&D pathway topic?
Cybersecurity is within plant modernization, but we don't specifically have a work scope that calls that out this year. That may be within another area. I'm not positive on that though.
There is another cybersecurity area in the nuclear energy enabling technologies category that's more general. Next question is the corrosion propagation rate included? And I believe this is probably the RC-9 scope.
I wouldn't exclude the corrosion, crack propagation for the type of study, but I think in the pristine stainless steel, the crack, the initiation would be more of technical focus or relevance.
Also for RC-9, are radiation effects under consideration?
Yes.
Frank, one more question on RC-9. Does it include corrosion mitigation strategies as well?
I think right now, based on my understanding, the FOA is more focusing on understanding the corrosion process damage mechanism and how the different chemistry and alloy microstructure would affect it. From there, the optimum outcome is if we can figure out a technique to mitigate the effect. That would be ideal, and I think it's probably part of the technumeric for consideration, but wasn't, I would say, isn't the first step in terms of this FOA, more kind of additional future research directions.
What type of results are expected from ICME modeling?
For example, if we can figure out certain effect of material microstructure, surface condition, the pH level of potassium, etc., on the corrosion rate, the crack initiation rate, etc., that will be considered.
Also on RC-9, is pitting initiation part of the study?
Initiation? I don't think so.
We'll have Allison and our TPOC stay on the line for about another 30 seconds or so. So please submit your questions now if you do have them. Why KOH, not NaOH? Is NaOH also of interest?
Not in this FOA.
Is swelling of interest in RC? They say RC 2.2, so I'm not quite sure what they're referring to. These work scopes that we're referring to here are RC-7 through RC-9.
Just for RC-9, swelling is not the focus of interest for this FOA.
That question was intended for the RC2 work scope. Please do tune in when the program manager for that work scope is available. Are material specifications for advanced manufacturing of interest?
Not in these work scopes. We do have an advanced manufacturing program within Office of Nuclear Energy that may address your questions.
That work scope will be discussed tomorrow morning. On RC-7, is an online decision-making tool expected as a potential deliverable?
It would be part of that effort, so it would show the application and what type of tool would be used to automate that process.
For RC-9, is this PWR specific? Will BWR conditions also be considered?
I think this is more PWR specific.
Okay, I believe that's all the questions we have. Thank you, Allison. Thank you to our TPOCs for answering questions. We will return at 1:30 Eastern Time for the RC3, which is the Liquid Metal Cooled Fast Reactor Technology Development Program, to give their presentation. So please tune back in at 1:30 Eastern Time. Thanks.
Thank you.